My name is Will. I'm here to walk through machine learning model selection using Metaflow. A week ago or two, the creator of Metaflow, Ville, gave a talk in this forum on Metaflow, its philosophy, its design, sort of high-level stuff, its roadmap. So that was sort of a high-level overview. If you're interested in Metaflow, please also go view that recording. This one is going to be a walkthrough. So we're going to do some coding here. And actually, you can follow, you can do the demo with me. So this is designed for you to, if you're in front of a computer and you have a terminal available and all that fun stuff, this talk is designed for you to go through this with me. We're going to do a quick setup of our environment. We're going to talk through what the example model selection flow does. And we're not going to run the full example because it's a highly parallelized job and I don't want everybody to drop off from crashing computers. So I'll leave that part to you, but everything else should be runnable by you during the talk, if that's at all possible. You don't have to do that, and I'll show you what kind of outputs you can expect in the talk, in the slides as well at the same time. So we're going to be switching back and forth just a little bit, and I'm happy to take questions during the talk, so please feel free to enter comments or questions into the chat, and I'll cross my fingers that I notice them. Cool. Yeah, there's some links I have to post here in just a moment. So very quickly about me, I'm a data scientist based in Los Angeles at this time. I was most recently at Netflix for a total of about 5 years. I also worked at 2 startups, one prior to Netflix and one in between. So I've worked in e-com, Netflix content, and ad tech in New York and Los Angeles. So that's sort of my machine learning professional history. Prior to all that, I did a PhD in physics with specialties in astrophysics and cosmology. So I did I spent a long time in school, and then transitioned from academia to the private sector to do machine learning stuff, like many people, about 10 years ago. I'm now at Discord. And my primary interests are some combination of machine learning and machine learning ops, or ML ops. So I'm really interested in shipping models out in production and productionalizing systems. That's one of the reasons I love Metaflow so much. So that's what I like to do day to day. And this talk is sort of right up my alley in terms of my interests. A little bit about Metaflow, you can read about it at metaflow.org and go view that talk from Ville last week or 2 weeks ago. It was created at Netflix, I'm going to guess about 5 years ago, 4 or 5 years ago. Ville was hired and started at Netflix after I was, after I joined. And he came and he sort of built this, this framework in a weekend, as the legend goes. And about 6 months later, I started to use it. So I started to transition over to using Metaflow. My job historically has been to build internally facing machine learning applications. So these applications are for business analysis, for internal use only, not for consumer facing stuff. So the requirements on scale, latency, and all that stuff are significantly lower. And in my experience, Metaflow, this is like the perfect application for Metaflow. For production systems that are consumer facing, when you're talking about millions or hundreds of millions or billions of users, and at the session level, even greater counts, then Metaflow may have its place, but you may need different systems there potentially. So I like to use Metaflow primarily for internally facing machine learning applications. So why did I make this blog post and talk? I'll point to the blog post in just a second, but I really liked working with Metaflow. Metaflow is exceptional in a few ways, and one of those ways it's exceptional is in the developer experience. It's extremely clean pipeline development platform. Very little, actually no interaction with YAML. It's pure Python interaction, and it's through subclassing. And it's a really wonderful experience. I also really like the people, the creators and maintainers. I really love their philosophy on developing software. They're just great to talk to, great to interact with, great to ask questions of. So they have a public Slack available. It's just like overall delightful. So highly recommend to engage with them actively. They'd be very interested in that as well. So I wrote this after leaving Netflix and before starting at Discord at my current job. So I had Metaflow on the mind and decided to write up a couple tutorials for fun. So we're going to walk through one of those tutorials today. So very quick outline of what we're going to do. We'll go through that setup in live, and then you can follow along too in a terminal if you want. Well, I'll sketch the demo of full scale parallel model selection. We won't do it because it would just crash all our computers. And then at the end, I'll highlight some of the implementation details in making all this work as they occur to me. And then, so to follow along, you can start here. This is the blog post that this demo is based on. And at the top, you'll see two links. You'll see a link to a GitHub gist, which is a recipe. Here it is. I'm going to zoom in a little bit. Yeah, that worked. So this is the demo. You can copy paste that as is, and I'll walk through the pieces. And then this is a GitHub repository that contains a package called Metaflow helper and these example workflows, one of which I'm going to walk through. So you can check that out. Actually, the Metaflow helper is on pip as well in v001. So that's one way to interact with it. But the examples you'll get from cloning this repository, we're going to do that together. And I think those are all the links you need. Let me just double check that. Yeah. All right, we're good to go. And one more bit of preliminary information. I'm going to talk about very quickly, I'm going to outline what this flow is going to do. So in this flow, I start by making a fake continuous variable regression data set using scikit-learn's make regression. Make regression is a really lovely way to mock data with known, characteristics. The demo is going to run LightGBM and Keras regressors in a tournament. Each regressor for each of those LightGBM and Keras instances is going to be run with different random hyperparameter settings. And for each of those settings, we're going to run n-fold cross-validation, 5-fold cross-validation specifically. Okay, so the parallelization, and this is one of the benefits of Metaflow, the parallelization will happen at that n-fold level. So for each of 2 regressors and 5 random hyperparameter settings for each of those regressors and 5-fold cross-validation for each of those grid points, that's going to be parallelized. So we have 50 parallel model training runs that we can run. And you can run it locally on the laptop. You can integrate with AWS and have those instances run in parallel in the cloud. That's where the real benefits obviously come from. But it's very useful to be able to run these things locally on a machine for debugging purposes. And we'll do an example that shows how debugging works. And then after all of that hyperparameter grid tuning, we'll pick the best model, do a final train test run to measure the model accuracy of the winner, and a final training run on the full data set. That's the model that you would ship into production. So that uses the whole data set, and you don't have a test set left over to validate. So that leverages the entire training set. It'll store a bunch of data and other artifacts. So it'll store a table to a file. It'll generate figures, and you'll see those pop up. And it'll store the objects for future retrieval. So again, Metaflow has a data store that that's part of the design, and so we'll store the feature engineering objects and the model objects for future prediction. Those are stored in the cloud on S3 if you're in AWS or in whatever cloud storage your provider uses. So that's an outline of what we're going to do today. So let's go for it. So rest assured, we're going to be using virtual environments. So you don't have to worry about this sort of clobbering your environment for the most part. We'll make a directory. Okay. So you can blow this entire directory away when we're done, and you don't have to worry about it messing with your system. We're going to git clone that Metaflow helper repository that I mentioned. So I'm going to copy paste this. So we're cloning that repository into this directory pretty fast. We're going to go into the repository, and we're going to check out the a pinned version. So I'm pinning to a certain commit that was released onto pip, and this is just for reproducibility. That produces this, which is we're pinned to a specific commit that was released. So hopefully that's fast and straightforward so far. We're going to create a Python virtual environment called venv. So this is a package, a module called venv, and it's going to create a virtual environment in a directory called venv. Takes just a second. So that created the files needed for it, but we have to activate it still. So here I'm going to activate. You know it's activated because this venv is prepended to your prompt. So now we're going to do everything inside this environment. We're going to pip install. We're going to do a bunch of fun stuff. Again, you don't have to worry about this messing with any of your other environments that you may have going. Pretty straightforward. So the package, Metaflow helper, is installable. And I'm going to install it in editable mode. That's what the -e is. So that means if I make local changes to the Metaflow helper package, they'll be immediately available throughout my virtual environment system without necessarily having to reinstall. So that's what -e accomplishes for us. And of course, I'm seeing a new error that I did not see before. Oh, and I didn't upgrade pip too. Very irresponsible of me. So we're going to do that really quick. Yes. It's recommended to use Python, the pip module as the CLI installer. That way you don't accidentally cross environments. And I'll reiterate that in just a second. Yeah, so let me just reiterate that. Python -m pip install is preferred over pip install alone because you can be sure that it uses the same Python environment as your Python executable, which for us is the virtual environment executable. So this is almost done. For those of you on Macs, I haven't come across this problem on Linux machines, but for those of you on Macs, you may also have to brew install LightGBM in order for the shared objects to be available. I'm on a Mac, so I'm going to do it. I've already done this, so it shouldn't do anything. But brew install, hopefully you have Homebrew installed already. Brew install LightGBM will put the shared objects in your Homebrew directory system somewhere. And then you should be set. That step is not needed in Linux environments from what I've seen so far. We're going to do one more thing. So we're running examples, right? We have a Metaflow helper Python package available. So that's a pip installable package. And then we have a set of example scripts. So those example scripts have different requirements than the locally installable Metaflow helper package. For example, Metaflow. The Metaflow helper package does not depend on Metaflow. The examples obviously do need it. So you will not have Metaflow installed until you pip install the example requirements as well, with a -R flag. Pip install -R. So this installs a few other things as well. And I don't think it'll take too long to get through. This is the final step. And that's it. Okay, so the environment should be set up now. Hopefully, at least one of you has tried to do this live. We can test the installation very simply by running a Metaflow script. So here we go. Model selection, train. And I'm going to show the CLI argument documentation with -- help. Let me first very quickly show you what this file is. So this is a Metaflow flow spec instance called train. Train is a subclass of flow spec, and flow spec is the basic class that you have to implement to get Metaflow to work for you. At the top here, you'll see a parameter called configuration. So that's a custom parameter that's exposed out into a UI if you use a UI, or the CLI, which I'm going to show you in just a moment. And here's how flows are implemented. Steps are decorated with a step decorator. You need a start step. In my start step, I create the fake regression data using scikit-learn's make regression. In the next step, you'll see for each contender. This is what I'm calling the grid points. So they're, it's LightGBM and Keras, and then hyperparameter points for each of those. I'm calling each of those points contenders. So it's contenders in a tournament. That's the metaphor I'm using here. And then I do for each fold. I told you that I do 5-fold or n-fold. The number of folds is configurable, cross-validation. That's in the for each fold. So these fan out into parallel steps, and they can be distributed in isolated containers in the cloud and locally in separate Python processes. So you'll see I'm doing some fun feature engineering and model training. And then this is the for each fold. This is the inner loop. This is the thing that fans out to 50 in the example, in the full example. I won't show you the rest of them, but this is basically how Metaflow jobs are implemented. And at the end, all you have to do is instantiate the class. Really easy. So I'm going to show you the CLI argument documentation that you can get by running that script, running that Python file as a script and asking for help. So it's going to take a moment. This is taking a moment because Metaflow under the hood is setting up its data store and some other things. That's a one-time thing, and it should be faster the second time. So that's just on first installation that it takes that long. So many of these arguments are default arguments. They ship with Metaflow, any flow spec, and some of them, one of them actually is a custom parameter that I showed you already. So so some of the, oops, yeah, here. So some of these are Metaflow. These ship with Metaflow. Environment, data store, you can ask for local or S3. So you can run locally and store results into S3 if you've connected it to your AWS account. There's the root path for the data store. Package suffixes, which you can ship out when you push into the cloud system of your choice. Piloting, coverage, all this fun stuff. I'm missing my configuration. That's okay. So those are that's how you can view the different commands that are available to you. So these are the high level commands that you would run immediately after here. So you could run your script with batch. You can just check. There's quite a bit you can do. You can run and you can resume your flow. So we will be running. Yes, that's why I didn't see it. So now I'm going to get help for the run command specifically, and that's where my configuration parameter that I specified becomes available. So this is the command we're going to run. I have to check something. I have to check the name of my configuration. It's test randomized config. So I'm going to run this configuration, which I specify with a string like this. Here we go. All right. So we're just about to run the example. Let me catch up my slides here a bit. We've pip installed. We've installed the example requirements. We've shown the help, the CLI help for the run command. And there are many other commands available to you. And we're about to run this example. This is the test randomized config run. So here we go. It's running a flow now. It does some DAG. It does some graph validation here. And it does some linting as well to make sure the code is well formed. And this is the flow running. So let's walk through what we're looking at right now. Workflow starting with a run ID. Here's a run ID. So looks like a timestamp. Presumably that's what it is. That's the ID of the run. So you run many times and you'll get a different run ID for each one. What this specifies is the step that's being run, and then this is the instance of the step. So steps can be parallelized, like I said. Oop, it's already finishing. So there's only one start step instance here. And the next step that runs here, the start task finished successfully. And here is the next step after the start for each contender. Looks like we have one two instances here, number 2 and 3. I think those are task IDs, yeah. And those are all unique apparently. So there are two contenders in this small scale example. There's a single LightGBM hyperparameter point, and there's a single Keras regressor hyperparameter configuration. So there's two models that are being run here. If I'm remembering correctly, I produce 1,000 fake data points, and I run against two models only, and I do one fold of cross-validation, so trivial. The idea is just to get this to run end-to-end quickly, not to do anything beyond that. The next step is for each fold. So I think we have one each. Yep, that looks right. We have end for each fold. So we collect the results over the end fold cross-validation in order to look at the variance of accuracy, in this case, R squared, over each of the fold points. And then we collect the results here and for each fold over the all contenders in the tournament here. So that's what it's doing. You can print any messages you like and many that you don't want. That's for end for each contender is what does that. Yes. Here's the train test run. Here's the full training run on the full data set, and then there's always an end step that finalizes. In this case, this is what the end step is what produces the charts. You'll see a couple things pop up in your browser if you do this. One is this. Let me increase the font here. This is model 0, model 1. Model 0 is the LightGBM regressor. Model 1 is the Keras regressor. And this is the score. This is R square score for each one. So here we have LightGBM is the winner, but this was a nonsense data set with bad hyperparameter values. So we're going to be rerunning this in full later. The other chart that this produces is the prediction versus the true value of that continuous variable. Yes. Yeah. So that's it. We've done a full run. There's another cool and useful thing that we could do, which is to visualize the flow. You can use GraphViz to view the DAG by running that kind of command, and then looking at the PNG output. So this is the flow that we ran. I've already described this a couple times. We start with start, and we go through contenders, folds. Then we end and collect the fold results. We collect the contender results in the tournament, do train tests, train, and end. So that's the full flow. Very simple, basic end-to-end machine learning training flow. Cool, we're almost done. I'll catch up the slides here on what we've done so far. So that's what it looks like when you're done. You hit the end step successfully, and then you're done. These are the charts that pop up in your browser automatically if possible. And this is how we produce the visualization. Yeah, contenders are points, hyperparameter grid points is the easiest way to think about it. So, so again, if you're doing hyperparameter tuning in scikit-learn, you'd use parameter grids. So that's basically what it is. And I can actually show you what that looks like in the example that we just ran. So here's the model selection example we just ran. And if you're familiar with scikit-learn's hyperparameter tuning, grid search CV or random search CV classes, you'll get this. Ignoring the complexity of these key names, you have learning rates for LightGBM regressor. And this is a random search CV. So this specifies the distribution from which learning rates are sampled. This is a log uniform between 10 to the minus 2 and 10 to the minus 1. Max depth for LightGBM, this is a random integer 1, 2, or 3. And estimators is always 10. The evalumetric is always MSE. And I'm doing early stopping both for the LightGBM regressor and Keras. And for the test configuration, I'm only doing two rounds of patients. Cool. Yeah, Python is fun. Yeah, there's lots of amazing tutorials out there to learn the basics of Python. And then there's some machine learning specific ones. The names are, I'm blanking on the names that I would suggest, but if anyone else has a suggestion for some of their favorite Python tutorials, please let us know. And then this is the Keras regressor instance in the contender spec. Yeah, so the loss function for the LightGBM was MSE. The loss function for, and that's on the validation set. Oh, I'm not even sure. Let's see if I can find out quickly. Yeah, Intel. Yeah, MSE in both cases on a held out set and with early stopping. So that's how the tournament is defined. So in this case, I do one iteration each. I can increase that to 50. So that would be 50 random samples from these specified distributions here. Yeah. Great. So this is the full demo, and I'm not going to run it because it's so heavily parallelized that it'll crash my computer. Probably. I don't even want to test it out. But I will say one thing, which is that you can control that parallelization during local debugging. Let me see if I can find it. Yeah, here. So the two flags I want to bring your attention to are max workers. So the maximum number of parallel processes, it defaults to 16. So if I were to run the full example for you right now, it would chunk through 16 parallel instances at a time, which is great. And it will work. It does work when I do it. It's just, it occupies most of my resources. So that's where the crash, that's why I mentioned crashing. Right. Yeah, and I did not enable GPU. Yeah. They can be parallelized on GPU. So let me be clear about this. For the step, and you can have different steps point to different instances in the cloud. So you can have the start step point to a CPU instance that's small, and then you can have like the training step point to a GPU instance that's potentially has more RAM and some other things as well, and which is really cool. So at the step level, you can specify the instance that you need in the cloud. I'm talking about when you run this in AWS. So you can actually parallelize across GPUs instances. So they're not within a single GPU instances. They're over as many GPU instances as your account can make available to you under the specifications. Yeah, I do. So regarding Airflow versus Metaflow, yeah, Airflow works. Airflow is like a proven technology. A lot of people use it for ETL as well as for machine learning. I'm currently using it at Discord for these purposes because we're on Google Cloud. And because that's the system that's in place. So they both work. Like I said, I think Metaflow really excels in developer experience and usability. You know, with Airflow, there's a lot of configuration that you have to mess with in different places. And in Metaflow, all configuration is exposed to you in decorators within the flow specs. So it's just the difference of, there's probably some other key differences, but it's mainly usability is one of the big differences, I would say. Yeah, thanks for that link. Yeah. Oh, Windows. I'm sorry, I've never tested this on Windows. So let me see what you're saying. FCNTL module. Very interesting. I would Google that. It's probably fairly common. Yeah, interesting. I'd be interested if you solved that, by the way. So anyway, if I were to run this for you now, I would maybe set n workers to 4 instead of 16. Nice. And then you can also set the maximum number of splits. So like I said, the inner split for this example, for the full example, is 50. I've gone up to thousands and 10,000 in real applications at Netflix. And so you can ask for that maximum parallelism to be 100 in cases where your true requirement is greater than that. And that just avoids breaking systems if needed. Ideally, systems would be able to queue things correctly for you, and there'd be nice, clean integration between them. But you at least have this lever from the Metaflow side to control the maximum number of parallel steps. Otherwise, you know, jobs can run forever. If you set this to 16 and you have 10,000 tasks that you need to run in parallel, it may take too long. And this is just sort of a fail-safe for you to error out elegantly. Cool. So that is the full example. Please go ahead and run it. That's what it looks like when it's done. And when I ran this on my MacBook Air, it took just over 20 minutes. When that's done, it produces those same figures, but they're not nonsensical anymore. It produces this predicted variable versus true continuous variable. So this is a nice regression problem. You can visualize an R-square. The R-square looks pretty good here. This black line is the one-to-one line. So that's the true relationship expected between true and predicted values. And you'll see this model tournament summary pop up as well. So this on the y-axis here is the score. This is the R-squared score in the case of the continuous regression. And these are the models. And it looks like there were, 10 models, 5 LightGBM hyperparameter settings, and 5 Keras regressor settings. In this case, LightGBM won quite handily. This isn't always the case, but this is often the case that LightGBM can beat neural networks quite well. Ooh, Ray, wow. Yeah, I came across it as recently as yesterday. I have not used it. Interestingly, I'm in the process with a colleague who's on the call actually of evaluating that for these exact purposes. So this is an open question that we're currently evaluating. CatBoost, yeah. Oh yeah, CatBoost, XGBoost, and LightGBM, all 3 of them are really lovely gradient boosted decision tree implementations. They're competitive with one another. but you can get one to beat the other at times. I like LightGBM for its speed, and I also like XGBoost quite a bit, and I don't have direct experience with CatBoost. Yeah, I'm available. Please reach out. High on Science, you'll see all my handles. You can DM me in whatever way you'd like. And then we can connect. Okay, so some key details. Yeah, sure. So some key details about the implementation that I want to highlight. I've already told you that there's a package that's installable that this example calls through imports in Python. So that's the structure of this. They're separated out, so they're actually independent, even though they live in the same repository in this case. And that's like a recommended pattern to use. Even though there's a global package, a helper package that's used, you still kind of have to find yourself having to implement sort of common functions anyway. So here at the top level, I'm going to go into examples, and then I'm going to go into this model selection example. And I have this common.py sub package here, sub module here. And it just defines these functions that are useful across Metaflow flows, but I don't necessarily want to like promote into the Metaflow helper package. That does happen. It happens quite a bit. And that is called like this. I will show you. So here I'm importing common. This actually should have gone on the bottom, but I'm importing common. And I'm also importing from Metaflow helper. So both patterns are possible, and a combination of them is probably ideal. So that's how you use common code. I have some other details about how to use helper Python packages in your Metaflow instances in the cloud. It's on my blog. I unfortunately can't get to it here, but it's possible to pip install from within Flow instances. It's not necessarily a recommended practice, but it's practical. Cool. And then another really, really cool thing about Metaflow is it's easy to debug flows in Jupyter Notebooks. So this is how you do it. You import step, flow, and run. And here I'm importing common, which is my local Python sub module that has all those utility functions. So I can test my utility functions as well. I've got auto reload enabled, so I can make changes to my files and they'll be immediately available at the cell level here. I have to specify that run ID. So I have to go back here. All you have to do is go into your run. Here's a run ID. And then you copy paste that into your cell. This lists all the runs available, and then you can ask for the latest successful run, or you can match your run ID. So here's one of the variables from one of my steps. So this step is the end for each contender step. And in .data, you'll have all the variables that you saved into the cloud or into your data store directly available. So .contenders is one of the variables that I saved in that step. And this is it's a dictionary or a list of dictionaries with these values. Okay, really cool. And you can do some really nice debugging in Jupyter Notebooks this way. So here are all the scores for every cross-validation instance, which you can inspect in notebooks directly. So you can inspect any step, any task within any step, and do some really nice debugging and development using those patterns. I think those are all the details I want to share with you. There are many more. You can read the blog post. I have a series on Metaflow that I hope to continue developing over time, where I talk about some of the other practices that I used to use quite a bit at Netflix. And I just want to highlight some possible extensions to these ideas, some of which I've seen, some of which I haven't yet. You could imagine, instead of using the best of a gradient boosted decision tree and a neural network, you can imagine ensembling them, and Metaflow, the patterns of Metaflow support that really easily. And so ensembling your best neural network and your best gradient decision tree in another downstream step, definitely possible. I didn't show an example of that, but I think you would just add one more step, or possibly a series of steps if you really needed to ensemble multiple models. And that could potentially give you accuracy gains if that's what you're looking for. So I wonder if that would win some Kaggle contests. Another thing I'm really excited about, and this functionality is not yet available, is versioning models using tags. It's possible to tag a run. Right now, the tags are immutable, but there's a request to make them mutable so that you can activate and deactivate runs and the data artifacts that go with those runs over time. So you can promote a model from test to production by just changing a tag. That's something that I've seen used, and it's a really great pattern to use. You can also do continuous deployment, and you'll see an example of this in the Metaflow directory, in the Metaflow helper directory here. I tried Circle CI, it works. They just wanted me to pay, so I stopped using it. And here I'm using GitHub workflows, and they did not ask me to pay to run parallel CI/CD jobs. So those are specified with YAMLs. Fun fact, I run the example that I just showed you in Python 3.6, 3.7, and 3.8 in CI/CD canary jobs using GitHub free. So there's a proof of concept there on how to do that. And then you can also publish, you can run unit tests and coverage tests, and then you can publish to PyPy as well, which I think I do here. Yeah, so you can also publish a package to PyPy in that way. So you can do all these, all the usual continuous integration and canary tests with these Metaflow jobs. And also another favorite practice of mine is continuous deployment. So every time you merge into master, you can have one of those CI/CD jobs deploy your master to, or main it's now called, to AWS or Azure, or in the future Google Cloud. So that's something that's been really helpful for me in the past. And those are all the ideas that I want to share with you. There are many more. It's a general purpose data pipeline framework, and really fun to use, highly recommended. And no, they don't pay me. And that's all I've got. Please feel free to, I'll stay here a minute or two. Please feel free to ask questions and connect on social media or elsewhere from my website. And thank you very much for attending. This has been fun. Oh yeah, here, I'll just do it one more time.
I didn't know if you wanted to kind of stay here for a couple of minutes. I could just talk to you about this very quickly here, if you would like. So I'm with a government contractor, and we're building a practice, a computer vision AI ML practice. And we're looking for strong computer vision and AI ML guys. And, you know, really one of the main reasons that I'm on here is really to network and see if there's anyone that is as talented technically as are you, to pass kind of the word around to see who might be interested and available. This is a, you know, the link I sent is the opportunity that we have. It's pretty detailed and remote
Great.
opportunity and highly compensating as well.
Thank you for sharing that.
No, absolutely. I just didn't know if whether it's you or anybody you know in your network that would be interested. I didn't see any other way to contact you, so I thought to just take the opportunity here to just talk to you a little bit about that.
Sure. I'll pass this around to any computer vision colleagues.
Yeah, and if you would like, I can actually in the chat send you my contact information right now, if I may,
Sure.
really quickly. Thank you.
Okay, thank you everyone again.
This is just my auto signature. I'm sorry, it's spaced out. But that's
Cool.
my name, my title, our address, phone number, website, and so on.
Thank you very much.
Thank you very, very much. Well, appreciate it.
Appreciate it. Thanks.
Great, thanks. Sorry about it. I just come back to grab a cup of coffee. So we're done with the talk. I see some questions, some of them.
I think we